In the last class, we discussed about something called as the Smith chart, that is the graphical tool for analysis of transmission lines for finding out different kinds of quantities. So what we saw was that the Smith chart is a very powerful tool and at the same time a very easy tool to use. Easy in the sense that you have to not do too many tedious calculations and rather just simply refer to that sheet and obtain the values that you want with a little bit of geometric constructions. Now, many people ask that which one should we use? Should we use the analytical approach or should we use the Smith chart? There are some people who really like to do number crunching using different formulae, and at the same time there are people who are interested in not solving equations too much but rather preferring the use of pictorial techniques to solve problems, for example the Smith chart. So my view is that a Smith chart is an easy technique but it is not 100% accurate. Reason is that obviously if you have seen the Smith chart closely, there are markings for all the R values and X values. Now there may be points which may lie between two consecutive R values and X values, and since the graph spacing in the Smith chart is not linear, there may be small errors which may creep in. So compared to that, using those big formulae like impedance transformation and whatnot, they may give you more accurate results. But if you want a quick result using if you want a quick result but you are willing to settle for slightly less accuracy, then Smith chart is very good. So today we shall look at a few applications of transmission lines. Now let's suppose I give you a transmission line. It has some length L and it is a lossless line with characteristic impedance Z0. So now if I connect a load impedance ZL, then what will be the impedance looking onto the other side of the line? So as you know very well by now, we can simply use the impedance transformation relation. So as you know, L is the length of the line and beta is the propagation constant. Now if you look closely at this quantity beta L, it is nothing but an angle. You know that the unit of beta is radians per meter and length is meter. So the product of the two will give you the units of angle or radian or whatever you may want to call. So degrees, radians, anything. Now this quantity beta L is often represented as theta, and this quantity is also called as electrical length. L is called the physical length or the actual length in meters or centimeters or whatever, and beta L is the electrical length. So if somebody tells you that, okay, I'm giving you a transmission line whose length is 45 degrees. Now you may think, oh my god, what is 45 degrees? Don't worry, it is simply theta. So it is for a given length and beta. So once you know the length of the line, you can find out beta. So, or vice versa. So now let's have a lossless line, and that implies Z0 is real. So now let us take a very special case. Let ZL be 0. Let ZL be 0. So what is happening? If ZL is 0, it means the load is short circuit. So if ZL becomes 0 and Z0 is some real positive quantity because it's a lossless line, then what will be Zin? So in that case, Zin, or the impedance looking from the other end of the line, will be what? Now if you apply this relation, ZL and ZL will get cancelled out because it's 0, and Zin will reduce to nothing but JZ0 tan beta L, or what we can also call JZ0 tan theta. Is that fine? Now let me ask, what is the condition under which this value Z0 tan theta will be positive? So when will Z0 tan theta be more than 0? So we know that Z0 is always positive because it is the characteristic impedance. Now what about tan theta? Tan theta can be positive depending on the value of theta. So I can say that this will happen when, let's say for a special case, theta is between 0 and pi by 2. That is when this entire term Z0 tan theta will be positive. So now if I say that Zin, that is nothing but JZ0 tan theta, and I know that Z0 is more than 0 and tan theta is also more than 0. So we have established the bound that 0 less than theta less than pi by 2, and theta you know is beta L, less than pi by 2. What is beta? Beta is nothing but 2 pi by lambda. So now if you simply put only L in the middle of the inequality and cross multiply, in terms of L, this means the physical length is between 0 and lambda by 4. So I can say as long as the line has length between 0 and lambda by 4 in the open interval, not equal to 0 or equal to lambda by 4, because if L becomes equal to lambda by 4, the tan term will become infinite because it will be tan of pi by 2. So if the length of the line is in this range, then I can say that this quantity is nothing but some Jx where x is more than 0. Now if I tell you, or now if I ask you, if some element or if some physical element has an impedance Jx where x is more than 0, is it something that we already know? Yes, it is. This is nothing but an inductor. As you know, an inductor has positive impedance Jx, or rather the X is positive. So this is very similar to inductive reactance. So I can say this Jz0 tan theta, or this positive quantity, is equal to some inductive reactance of some inductor, which is nothing but 2 pi Fl, where L is the equivalent inductance. So if I simply cancel out the J and I solve for L, that means L will be equal to nothing but Z0 tan theta divided by 2 pi F. That means if I have a transmission line of lossless transmission line of impedance Z0 and it is terminated by a short circuit and its length is between 0 and lambda by 4, then this impedance will exhibit an inductor. So it's like saying it is similar to this. So simply by using transmission line, we are realizing the value of an inductor. And that is amazing. Because for many applications, you may not get the value of inductor that you want. So in that case, you have to resort to either using series combination, parallel combination, or if it so happens that the value of L that you want is very high or very low, in that case, using transmission line to realize an inductor is a very, very interesting approach. Now, let us look at this exact same thing, but by using the Smith chart. So, as you know, this is the Smith chart. So, we were talking about having a transmission line which has a short circuit load. Now, what is short circuit? Short circuit is this point. Short circuit is this point. Now, as I am moving away from the load, so essentially what I'll be doing is I'll be moving along the outer periphery, because now my VSWR circle would be this big circle. So if I start moving from this point clockwise and I stop at a point before lambda by 4. Now where is lambda by 4? If you see, the marking is 0 over here for the wavelength marking, and here it is 0.25. So as we had proved in previous classes that the opposite diametrical ends of the Smith chart or the VSWR circle indicate a movement of lambda by 4. So therefore, as long as I am not coming at this point, I will be somewhere on the upper periphery of the Smith chart. And as you know, the upper periphery indicates an inductive reactance. So therefore, if I have a short load, a short circuit load, and I am moving on the line but within a length of lambda by 4, I shall always see some inductance value. Is that fine? Now, if I have the same transmission line but it is now open-ended, that means its load is open circuit. Open circuit is here. Now, if I start moving from the open circuit away from the load, I shall be on the lower periphery of the Smith chart as long as the distance I move does not exceed lambda by 4. So therefore, in that case, the impedance I will see will be capacitive. So let's write it down. If I have a transmission line, lossless transmission line Z0, and I have this ZL which tends to infinity. That means it is open. So in that case, Zn will be what? If you apply theta is again beta L. Okay, and let us say that again this length is somewhere between 0 and lambda by 4. So what I can do, I can simply take ZL common. So this will be nothing but Z0 1 plus Z0 by ZL tan theta Now here if I put the limit of ZL tending to infinity, so this term and this term will cancel out, and what I will have left behind is only Z0 by J tan theta. Again, this entire term will be positive only when theta is between 0 and 90 degree, or the L is between 0 and lambda by 4. So this is very similar to having a capacitive reactance. So if you just cross multiply, you can realize any value of capacitor through this. So again, you can realize inductor and capacitor, or rather you can realize a capacitor just like the way we realized an inductor, but using a transmission line. But this time you have to keep the load as open circuit. So just to repeat what we have been discussing, if you start from the open circuit point and move away, but you don't move more than lambda by 4, then in that case your impedance will always be purely capacitive. You will always be on the outer periphery of the lower half of the Smith chart. So that is how it is. Now we saw one application of a transmission line, and that is a rather useful one, where you can actually realize inductors and capacitors using transmission line. Now let us look at the other application. Now what we will do is we will simply use the same concept what we used, that is having a transmission line with either an open load or a short load. So let us go for the same transmission line and let's assume a short load. Again lossless, ZL is 0, Zin. So this is theta equals beta L. Let's not get into the exact length of the line at this point, but rather formulate what the input impedance is going to be. So as we proved, this is nothing but JZ0 tan theta. Now let us look at the mod of Zin. That is nothing but Z0 tan theta, or Z0 tan of beta L. So let us plot this in the form of a graph. This is L and this is, or let me not say the mod, let me say the imaginary part of Z. that is only z0 tan theta. So let us plot what is this imaginary part of z in as a function of physical length L. So let me mark 0 over here, lambda by 4, this is lambda by 2, this is 3 lambda by 4, and so on. So this should not be very difficult for you. It is nothing but drawing or sketching a trigonometric function, the tan function. So when L is 0, this will be 0, this quantity. What about lambda by 4? When L becomes lambda by 4, theta becomes pi by 2. So therefore at this point, the tan function will tend to infinity and become a discontinuous function. So let us draw that. It will look something of this kind. Likewise, you can draw for the rest of the L axis. When L becomes lambda by 2, theta will become pi and tan of pi is 0. So therefore, the graph will be something like this now. So now let L be exactly equal to lambda by 4. So what will happen? I have a transmission line which is terminated with a short circuit, and L is exactly equal to lambda by 4. This is Z0, this is Zin. Now, what will be Zin? Obviously, Zin is something you can see, not quite discernible from the graph, because slightly left of lambda by 4, it goes to plus infinity, and slightly right of lambda by 4, it is starting from minus infinity. So, it looks like an open circuit, yes. But as you know, open circuit is plus infinity. Okay, so in some sense I can say that if I am just delta left of lambda by 4, I will come to an open circuit. But having an infinite impedance in magnitude definitely gives us an indication of an open circuit. But is that all it does? What happens? We had proved that when the length is below lambda by 4, as you can see, the impedance is positive, so therefore it behaves like an inductor. And when it is more than lambda by 4, at least in this part, until lambda by 2, this behaves like a capacitor because of the negative impedance value. So this is purely capacitive reactance, this is inductive reactance. But what is happening at lambda by 4? It is neither inductor nor capacitor. So it is like saying you are now at this point where earlier your reactance was positive, now it is going negative beyond this. So in some sense, it is a cross between an inductor and capacitor. But what exactly? What combination of inductor and capacitor will give us an infinite impedance in magnitude? We will get infinite impedance when we have an inductor and a capacitor in parallel, and only if the two are in resonance. That means the impedance, the parallel impedance becomes so large that this acts like an open circuit. So if you want to realize a parallel L and C resonance circuit, all you have to do is take the transmission line, make its load equal to 0 and ensure that its length is exactly equal to lambda by 4. That's it. So this is nothing but parallel resonance. That is this point. So now, if we have discussed about parallel resonance, there must be something called series resonance also. Now, series resonance of an L and C happens when the two reactances cancel each other. Now, you can say at this point, the impedances are cancelling each other. So therefore, if I have a transmission line Z0, which is again short-ended and its length is exactly equal to lambda by 2, this is like saying, it is like saying that this exhibits a similar phenomena to that of a series LC resonance. So there are many applications where we use series and parallel resonance, most notably in the design of filters. Whether you want a band pass filter, a band stop filter, looking at that, you may want a series resonance or a parallel resonance. So discussion of filters using transmission lines is a little beyond the scope of this course, but I strongly encourage you all to look it up as to how we can design filters using LC resonance and whether we can design those resonances using transmission lines. So, what we have seen so far, we saw two applications of transmission lines. The first was where we are able to generate or we are able to realize an actual function of an inductor or a capacitor using a transmission line that is short circuited and whose length is also thought of in an intelligent manner. That is, its length should be below lambda by 4. Not only that, we saw the second application, which is an extension of the first application. That is, we are not just able to realize inductors and capacitors. We saw that when you have a short-ended transmission line whose length is below lambda by 4, it acts like an inductor. Likewise, we saw that when we have an open-ended line whose length is below lambda by 4, it acts like a capacitor. But a short-ended line whose length is equal to either lambda by 2 or lambda by 4 acts like either parallel resonance or series resonance, depending on what the length is. So you can realize not just inductors and capacitors, but you can also realize resonance phenomena. And that is very useful for many applications. Now, let us briefly discuss the third application, which is a little bit not related to this particular discussion or this particular application. Now, when we had discussed about transmission lines, let's say there's a line, lossless line for example, and this is terminated with some load ZL, may be real or complex. Real or complex, that we don't know. But depending on the type of load, a standing wave pattern gets formed on the transmission line. So therefore you may come across some point where you get some Vmax, you get some point which is Vmin, again you get a Vmax. It depends on several things, but one thing we know that this distance is lambda by 4 and this distance is also lambda by 4. Now the question is, how do we measure these voltages? So how do you measure voltages in the lab? You simply take a multimeter and you connect it across the 2 points whose potential difference you want to measure, or a voltmeter. That's how you do it. But that is not the case with transmission lines. If you keep a voltmeter, the probes of the voltmeter will also act like a transmission line. And therefore, the wave will now go in 2 different directions, and you will get one part of the wave will go to the load, one part of the wave will go towards the multimeter, and therefore all the values that you want will not be available, and all these values will change, and there will be some reading which you will take on the multimeter which is incorrect. So this is not the way we do. So the way to measure these voltages is to use something called as a slotted line. Where you take a voltage probe and move it along the line, but you don't physically touch the line. It is like saying you have a voltage probe which is close over here, which is movable. You can move this voltage probe along the line where a small opening is made, which is called a slot, for the probe to move. So without physically touching the line, this probe can move backward and forward, and it can sort of tap what is the effective standing wave voltage on the line. Okay, so there are setups for slotted lines, and we do have them in our lab, but understanding how slotted line works is again beyond the scope of the course. But I have given you a very basic idea behind how the slotted line is working. So now let us say I have a slotted line, I have a voltage probe through which I can measure these voltage maxima and minima. Now the question is, if I know the voltage maxima and minima, can I know what is ZL? Can I know what is the load that is connected to the line? Now many a time what happens is that there are transmission lines where the load is really far away from you, or the load is buried, or it is inside a case which you cannot open. In that case, without having physical access to the load, how can I measure, or how can I at least know what type the load is? Fine, I really don't have to know the exact load. That's fine. That I can find out later. But can I know at least what kind of load it is? It could be purely resistive. It could be purely inductive. It could be purely capacitive. It could be some R plus Jx, where X could be positive or negative. So there are multiple possible values that the load can take. So now let us ask ourselves, if I can measure these voltages and voltage maxima and minima, or some nature I know, where the load is not physically accessible to me, then can I know what is the value of load, or what is the type of load? So let us say unknown ZL. We don't know what ZL is. We all know that it is, let us say, kept right next to us, but it is inside a casing, or it is buried below the earth. Let us say we have access to some points which are close to ZL but not exactly ZL. Okay, so now Now suppose I am at the load. My voltage probe is at the load. And I don't know what the exact load is. And I now start moving this voltage probe to the left. And while moving, I see that the Vmax is happening exactly at the load. So some Vmax is happening here and some Vmin is happening here. Again, after some time Vmax will come, and again after some time Vmin will come. I am just drawing the magnitudes. So from this, what can I say about ZL? Fine, I may not know the values which comes later, but can I say anything about the load? Yes, I can. We can use the Smith chart to do this. What I am observing is that when I am at ZL, I am also getting Vmax at the same point. So now, suppose my load is somewhere. There will be a VSWR circle. There will be a VSWR circle. And the point, let me just draw it separately. This is the Smith chart. Let us say this is the VSWR circle corresponding to that load. Now the load can be anywhere on this dotted circle. So if I know the VSWR circle, can I say which point I will get Vmax? Yes, I can. I know that this is the point where I will get Vmax. And this is the point where I will get Vmin. So I am observing now that Vmax is at the same point where the load is. So therefore this point will be small zl. Because my load position and my voltage maxima are intersecting. So I can say that this load impedance is purely resistive. Because the voltage maxima is coinciding with ZL. Now what if we had a voltage minima over here? What if it would be like this? If the voltage minima was coordinating or coinciding with the load, in that case my load would have been here. Again it would have been purely resistive. So whenever the load position coincides with either a voltage maxima or a voltage minima, the load is purely resistive. Okay. So you can have resistive loads with two different conditions, either a Vmax or a Vmin coinciding with the load. Now, again, let us say I have a transmission line which is terminated with some unknown load ZL, and I observe some voltage which is not a maxima, neither a minima. So some voltage I observe over here, but as I move away from the load, the next point of interest I observe is a voltage minima. The maxima can be somewhere later. This point is neither maxima nor minima. But a short distance away from the load, I encounter a voltage minima. So can I say what type the load is? Now again the load will have some VSWR circle. Let us draw that. Now where is the voltage minimum? Voltage minimum is here. Voltage minimum is here. So after moving some distance away from the load, I encounter minima. That means I must have started from somewhere over here, the below part of the circle, because I am moving clockwise away from the load and suddenly I encounter a minima. We know that this voltage at the load is neither maxima nor minima. That means the first point, the first extreme which I am encountering is a minima. We know voltage maxima is here. So definitely this load cannot be here. We are observing a voltage minima, let us say, which is not equal to 0. Some positive or some non-zero quantity. So if my load is over here, only then the first extreme point I can encounter is a minima that will happen only if my load is on the lower part of the VSWR circle. And this voltage minima, as you know, it is not 0. So that means this is some resistance plus capacitance. This is it. Because we are on the lower half of the Smith chart. Now, what would have happened if the same point I would start some non-zero voltage, but the minimum would have been a 0? The voltage minimum I am encountering next would be a 0. In that case, our VSWR circle would coincide with the outer periphery of the Smith chart, or the gamma equal to 1 circle. In that case, our voltage minima would have been here. So that means the load would be somewhere on the lower periphery of the Smith chart. So in that case, it would have been purely capacitive. Now I leave it to you as an exercise to think of other possible maxima or minima that you can encounter, whether it is 0 or non-zero, and thereby try to identify if the load is inductive, purely inductive, or has some resistance plus inductance component. So today we saw a number of applications of transmission lines, including realization of LC individually or in the form of LC resonant circuits, and also we saw one very useful technique through which, if we look at the voltage maxima or minima along the line, we can identify what type of load it is. So with this, we shall stop here.